In this talk, I'm going to talk about work in progress together with Rafael Alvarez Garcia, who is now a PhD student in Hamburg. What we wanted to do is we wanted to compute distances in the moduli space of Calabi-Yau manifolds analytically and use this to challenge the swampland distance conjecture. But we soon realized that there's a really fascinating underlying structure and class of identities known as the generalized Clausen identities. So this talk will be about these identities and how to use them to compute periods analytically and to use this to compute distances analytically. So let me start by reminding you what the distance conjecture states, and especially a very refined version of this conjecture. It states that there is an infinite tower of states which appears when one moves beyond of order m Planck in the moduli space, and this tower becomes exponentially light with the distance. So effectively, the conjecture states that we have the following mass relation. It's an exponential decay with an order 1 constant alpha, and it goes with the distance in moduli space. Of course, this distance has to be measured along a geodesic. If we want to measure a distance like this, we need the metric on the moduli space. As the moduli space is a Kähler space, we can express the metric as the second derivative of the Kähler potential. And the Kähler potential, in turn, can be expressed using the periods of the underlying Calabi-Yau manifold we are interested in. The problem here is that we actually need global expressions for the periods to compute the distances exactly. One can do it numerically, but if we have more than one modulus, the convergence is really bad. And actually, Daniel Kleve has recently computed some of these expressions using heterotic duality and found a rather large disagreement between the numerical results and the exact results. So local expressions are just not enough because we need to move close to phase boundaries like conifolds, etc. And then we can get rather bad convergence problems. So the goal is to compute closed forms which are globally valid across different phases and not only in one phase like around the LCS or around the Lano-Ginzburg point, but all over the moduli space. So just to set the stage, for the moment, I will be looking at Calabi-Yau hypersurfaces or complete intersections in weighted projective space. We choose a symplectic basis of the middle homology, and then we integrate the unique holomorphic freeform over the spaces, and we get the period vector in symplectic form. And this is exactly the object we are after. Independent of the basis chosen, this vector is annihilated by a system of differential operators known as the Picker-Fuchs system. This system only depends on the charges of the GLSM describing the Calabi-Yau or the relations between vectors of the toric construction, depending on which point of view one takes. So this is known for effectively any Calabi-Yau one is interested in. So the only task we have is to solve this system here. A closed form around the large complex structure point was already given back in the 90s by Hosono, Clem, and Tyson, where they give an expression in terms of an infinite sum. So for each complex structure modulus, one has an infinite sum over a certain combination of gamma functions. This here is the so-called fundamental period denoted by omega 0, and it includes some deformations by so-called indices rho I. These indices are introduced such that one can take derivatives with respect to them, so that one gets the complete period vector and not only the fundamental period. This looks like that. One defines 3 differential operators with up to third derivatives with respect to these indices. These operators depend only on the classical intersection numbers, and it gives us a complete basis around the LCS point. What one can do now is, if we are at the boundary of a moduli space, for example, for a 3-parameter model, we can resum one of the coordinates into a hypergeometric function. And if we are at the boundary, like all of these contributions here vanish if x and y would be 0, so only the n1 equals 0 contributes. And then the fundamental period just becomes a hypergeometric function. Thus, in this case, we would need up to the third derivative of this function with respect to its parameters a and b, where the indices appear again. This type of derivatives are the so-called epsilon expansion of hypergeometric functions. These are really well studied in the amplitudes community because there this epsilon stands for the deviation from the 4 dimensions. So in dimensional regularization, one writes 4 minus epsilon, and this is this epsilon here. So it's really, really well studied. But more recently, the mathematicians have taken over. So for the last 7-8 years now, they have many results for these epsilon expansions, but it's still a really hard computation. So if you are given any hypergeometric function, you will probably not be able to compute its epsilon expansion unless it's a really special type of hypergeometric function. Luckily for us, these special types are exactly what we are going to need. For example, in the easiest cases, there are exactly 4 complete intersections which result in elliptic curves. So I have given here the 4 embeddings in weighted projective space. And these 4 correspond to these 4 fundamental periods. All of them are 2f1 functions, and the parameters appearing are of this form here. So we have only one parameter a, the second parameter is 1 minus a 1, and then the argument, so the complex structure modulus. This is a really, really special case of hypergeometric functions, the so-called Legendre family, because they are rewritable in terms of Legendre functions. And moreover, the special cases with a equal 1/2, 1/4, 1/3, and 1/6 are exactly matching Ramanujan's theory of elliptic functions of alternative basis. So this one here is the complete elliptic integral of first kind, and these are the 3 higher or alternative basis versions of this integral. Now, when we want to compute its epsilon expansion, what we actually need to do is to compute the derivative of this function with respect to rho. But note, here's a 1, here's a 1 plus rho 1. So if we set rho 1 to 0, this one cancels this one. So we actually need only the derivatives of this function, which we just have discussed. If we write the hypergeometric function out in its infinite series form, one finds the following form here, and taking the derivatives of the gamma functions gives us some bi-gamma functions. These sums are rather complicated to evaluate, but one can rewrite these d-gamma functions in terms of certain harmonic numbers. These harmonic numbers, on the other hand, have some nice identities which can be used to remove these fractional harmonic numbers and to rewrite everything in terms of just integer harmonic numbers. And all of these logs which appear here actually cancel out in the end due to some structures appearing here. And the end result is actually much easier. So the first derivative of the fundamental period is just of this form, and these sums are well studied by number theorists and are known as so-called twisted hypergeometric sums. And actually, in this very easy case, the generating functions are actually known, so we can resum this sum by using some binomial representations for the gamma functions in terms of complete elliptic integrals. So just to recap, we had a complete elliptic integral and wanted to compute its parameter or epsilon expansion. And this expansion turns out to be expressible purely in terms of the same complete elliptic integral and some logarithms. No more complications are arising. Even better, rather recently, Nicholson and Blaschke have computed the analog for the alternative basis, or more generally for the whole Legendre family. But they found that the parameter derivatives are evaluatable purely in terms of the same functions, some rather complicated transcendental numbers, but it's just a number for any value of a parameter a, and logarithms. And moreover, all these transcendental numbers simplify drastically if we insert the values of a appearing for the 4 elliptic curves. Now, if we use all of these identities, which are probably rather complicated, we obtain in the end a closed form for the periods of the 4 elliptic curves. For example, for the simplest elliptic curve, which is the 1/2 parameter, we find that the mirror map in the end is expressible purely in terms of the ratio of 2 complete elliptic integrals and a very simple transcendental number, and that's it. This form can actually be obtained otherwise also, not using this hypergeometric machinery, because we know that the mirror map is the inverse of a triangle map. And these triangle maps are well studied, especially in the 80s and 90s, and one gets exactly these ratios of hypergeometric functions as the inverse of triangle maps. But the nice thing about this here is that it will generalize directly to K3 manifolds and multi-parameter models, which is rather nice and there's no analog of this expression known for these multi-parameter triangle maps. So in the rest of this talk, I will show you how one can use this result to compute the periods of K-free manifolds and even Fano-free folds in closed form only using these results. How is this done? So the first observation is a very, very classical identity by Clausen, already nearly 200 years old. This identity relates the square of a 2f1 function to a 3f2 function. And the nice observation now is that this 3f2 function here is the fundamental period of a certain class of K-free manifolds, namely a class which appears as a fiber of the standard examples we use in string theory, for example, P11222 or the octic inverted projective space. But this identity has a slight misalignment of the parameters. So it relates a parameter A to a function with parameter A half. And this is not so nice because we don't know the abstract expansion of this function. But there is a rational transformation of the right-hand side here, which turns it back to the 2f1 function with parameters A and 1 minus A, where we just have computed the epsilon expansion of. This identity here is known as a symmetric square, and I will call these types of identities a twisted symmetric square. So a symmetric square where we are allowed to add a rational transformation of the argument. The nice thing about these identities is that they relate the fundamental period of certain K-frees to the periods of elliptic curves which are known. So we know the periods of a K-free also in closed form when we know the periods here on the right-hand side on a closed form. And even better, the structure is such that this does not only work for the fundamental period, but also for the first epsilon derivative. Sadly, the second derivative does not work out because here some epsilons are placed such that they break this relation. But there's another identity helping us out here, the so-called period identities. Now let me give first a rather physical explanation where these identities arise from. Namely, if we compactify on a K-free manifold, we will have a resulting n=4 supersymmetric theory. This amount of supersymmetry means that there will be no instanton corrections to the prepotential. But if we would allow for a general form of the periods, these corrections would be there. So this gives us a constraint or condition on the periods. And if one works it out, one sees that the second period needs to be related to the square of the first period over the fundamental period. So this means in turn that the knowledge of the first two periods is sufficient to compute everything. And the first two periods are exactly obtainable by Clausen's identity. So in effect, everything is known. As a side note, both relations, the Clausen's identity as well as a period relation, follow directly from the fact that the Picker-Fuchs operator is the symmetric square of the second order operator of the elliptic curves. Because this is actually an identity not only between the operators, but also between the solutions of the operators. And the solutions of the second order operators can be always combined to form all solutions of the third order operator. And so we actually will not generalize this idea here, but actually we'll be looking to generalize these twisted symmetric squares. But before we do this, let's go to an example. One of the most classical examples of a Calabi-Yau is the octic in weighted projective space. And this is also one of the examples Daniel Claver recently computed this distance here analytically using heterotic duality. So how would we go on to compute this distance? First, we know the prepotential as we have n=4 supersymmetry. From this and the classically known topological numbers, we can compute the periods. From the periods, we get the Kähler potential, and from the Kähler potential, the metric. When we take the limit of T2 going to infinity, then there's only one leading order term independent of T2 surviving, and this is given by 1/2 times the imaginary part of the other modulus squared. Thus, we only need to integrate over this metric to get our distance we are interested in. Now, the coordinate system here is built as follows. So here's the large complex structure point, which is x=0, when we will have x=1 here and x=infinity here. So we just need to integrate from 1 to infinity and we are done. But of course, we actually know the metric on the Kähler side. So what we need to do is we need to compute the mirror map. The mirror map itself is given by a ratio of periods, so by the ratio ω1/ω0. we express all of these periods using this generalized Clausen identities, insert the closed forms I have given you before, and then putting everything together after a 3-page long computation, you arrive at this closed form for the mirror map. Now everything is simple. You just type this into Mathematica and integrate from 1 to infinity, and you get in an analytic closed form the distance, which is in complete agreement with the heterotic prediction. Let me say some comments to this example. First off, there are no logarithms in the mirror map. Usually, if one writes down a mirror map, one writes down something like logarithm plus infinite series. But this infinite series is exactly of the type that it combines with a logarithm to form these complete elliptic integrals. This is of course needed because if we expand the periods around the conifold, there is no log. So if we want to have a general expression valid all over moduli space, of course the log has to combine with the infinite series, but it's still interesting to see how this happens. Secondly, all of this is of course underlined by modularity, but we neither used nor needed the modularity, so we will be able to generalize it beyond the modular cases. In this example, the mirror map is actually long known from the 90s already in terms of modular expressions given by the J function of gamma 0, 4. But this J function is incredibly complicated and given by a certain combination of theta functions. These theta functions are hard to invert, and we would actually need the inverse of this relation. So we need t1 of x and not x1 of t. So this is a horrible task. And I don't think it's possible to do it analytically if one does not know this hypergeometric treatment, but extremely good approximation are actually possible. See Daniel's talk given actually here in the seminar series some months ago, which only use cosine functions. But the advantage of this hypergeometric treatment is that one directly gets the inverse relation. So this means this expression here is the exact inverse to this modular relation given here. Okay, so now how can we generalize this to more complicated geometries and even beyond complete intersections or to multi-parameter models? So for this, I need to do a small aside, and these are the so-called Aperi-like sequences. This sequence here was used by Aperi in his proof of the irrationality of zeta 2. Of course, zeta 2 is just pi squared over 6, so it was long known that this is irrational. But the complete analog of this proof works for zeta 3, and this is why these sequences became so famous. This sequence follows a certain recursion relation with certain values of parameter chosen, and all of them are integers. This observation inspired Sagi to search for more sequences of the same type. That is, they are only integers and they follow a recursion of this type for some other parameters than these. Moreover, if we search for the generating function of this sequence, we find a function which will fulfill this differential equation here. And this looks rather closely like a Picard-Fuchs equation. Put c equal to 0, you have exactly the hypergeometric equation which we had up to now. So this is a direct generalization to more singularities of the curves. The results of Sagi then were 6 sporadic cases. So we found the hypergeometric cases, he found the Legendre cases, and he found these 6 solutions and gave them the rather uninspiring names A to F. These sequences have some rather interesting properties. So of course they are all instantons, so they are candidates for mirror maps or periods. And moreover, they all have the same hypergeometric functions appearing, which are of the form a, 1 minus a, 1. So exactly the same form we already had. It's only appearing some rational function in the argument and a rational function in front.
Lorenz, you have 5 more minutes.
Thanks. So these sequences actually turn out to be the periods of the 6 curves with 4 singularities. These curves were classified by Boykers, and it was realized how they are related to these 6 sporadic sequences by Sagi himself. The nice thing is we have closed forms for all these sequences, and they are exactly of a type whose epsilon expansion we can compute. So these now form a nice basis of functions we can use to compute the twisted symmetric squares of and compare them to the Picard-Fuchs operators of K3s or Fano threefolds. And the really nice surprise is that actually they are enough to compute all K3s and Fano threefold operators I could find in the literature. So all geometrically known K3s can be computed in a closed form. This works as follows. So this is again the Picker-Fuchs operator, which annihilates these sequences. Van Straten and Sudilin found the following symmetric square relations, which then relate the solutions of this system to the solutions of this system here. The details are not so important, but just note that it's always of the following form. We have A, B appearing at the X coefficient, and then we have a cubic polynomial in theta with the C coefficient. If we now, the Clausen's identity has exactly the same form as these generalized Clausen identities. But if we now look at the lists of K3 manifolds, for example, the one given by Li and Yau in 1905 about diagonally constructed K3s, we find a perfect agreement. The forced Fur cases here are the hypergeometric cases given by the classical Clausen identity. And now, if you look at all these others here, we find we have this cubic polynomial with some constant in front, A, B, A, B, A, B. It's always the same structure. So all of these operators are actually expressible in this form here. And as these identities can be rewritten in a form that the solution of this identity is given by the square of a 2 of 1 twisted with certain coefficients, we actually can compute the epsilon expansion, and so we are done. We can also look at certain lists of Fano freefolds. So these were listed by Golishev in 2005. They are actually classified. There are only these 17 one-parameter Fano freefolds. And the structure is completely the same. It's not so surprising because these Fanos are mirror symmetric to K3s, but still, as they are classified, we can go through the list and we find exactly the same structure. There's AAB, and a cubic polynomial. So we can map them using this twisted symmetric squares. So finally, the last point is multi-parameter models. So far, I have only talked about a single parameter, but the multi-parameter case works exactly the same thing. We need two different relations. First off, a relation relating the second period to the first derivative periods. And we need a generalization of Clausen's identity relating the solutions. This generalization of the period relation was already given by Hosono in 2000. It's exactly of the same form. It's just not W1 squared, but now a combination of all W1s appearing in the numerator. And for the generalization of Clausen's identity, I will just give an example here for the degree 24 hypersurface invaded projective space. If we take one of these parameters of this 3-parameter model to infinity, we will get the following Picker-Fuchs system. So this system is a 2-parameter Picker-Fuchs system describing a K3 manifold. The solutions to this system are purely expressible using W0 and W1 of the A equal 1/6 hypergeometric elliptic curve. Using these two, one can find certain rational transformations given by the solutions of this system, such that all combinations of W1 and W0 are solutions to the system. It's given in this rather strange fashion because the actual solution of the transformations are horrible. They fill like 2 pages of square roots, but they are all algebraically and can be given in an analytically closed form. And with modern computer systems, one can integrate all of them without any problems. So even multi-parameter models are doable as long as we are dealing with K3s. So let me finish up. What I have shown you is that we can compute closed forms for the periods of K3s and Fano freefolds using a hypergeometric treatment. And this is effectively exactly the inverse of the usual modular relations we are using. The results obtained by this, for example, for distance computations, agree with the results obtained by heterotic duality. But sadly, so far there are no known Calabi-Yau freefold examples in the literature. The reason for this is we need now to not look at symmetric cubes, but squares, but symmetric cubes. The problem is the symmetric cubes do not give Calabi-Yau operators. We really need this non-twisted factor to come in to get the Picker-Fuchs system of Calabi-Yau freefolds. And the computations become really tedious. And actually the computer at the moment just explodes if you want to try these computations. But we are still trying to work this out. And of course, I have only going to second order in the quadratic equations. So this is 4 singularities of the elliptic curves. One, of course, could also study 5 or 6 singularities, which then correspond to recursion relations with more terms appearing in the recursions. And this is actually a project we are planning to do. But in principle, it should be, this should give an extremely strong computational control over fibers of Calabi-Yaus, which can not only be used for the distance computations, but also for moduli stabilization, for example, close to the conifold, where one now does no longer need to expand in the moduli and thus gets a constraint how far from the conifold one can move. Because one has a closed form, this does no longer give any constraints on the fluxes. That was all I wanted to say. Thank you.
Great, thanks a lot. Let's do the clap emoji for the Lorenz. And now we're going to open up the floor for the questions. So if you have any questions, please ask. Okay, maybe I can ask one question. So it looks like the fact that you're dealing with the Fano threefold or the K3 manifold is very important. Do you think you can utilize some K3 fibration in some Calabi-Yau threefold or the fourfold to simplify the computation of the Picard flux using the method that you've been describing?
So we are actually exactly started by looking at vibrations. So as soon as you have a K3 vibration, a Calabi-Yau threefold, you can compute some of the periods of this Calabi-Yau threefold. But of course, you cannot compute all periods. Especially, there's always the period like orthogonal going in the P1 direction, mostly in this case of the K3 vibration. And this then is no longer computable in closed forms. And then you need to do a power series again. But of course, this helps you also with computing the fibers.
Mm-hmm. Is there any question for Lorenz? Okay, then let's move on to the next speaker. Thanks, Lorenz.